Hi folks, we're going to take a look at the solution to page 158, number 18 from the Unit 4 assignment. So it's a pretty typical type of question where you're building some structure that has different costs for different parts. In this case here, they're building a pipeline that can go underwater or that can be built along dry land. Okay, and the difference is they don't give us the exact costs for each, but they tell us that underwater is 60% more than dry land. Okay, and what we have to do is we've got to cross a 1 kilometer wide river and then go 8 kilometers down the river. Okay, and the idea is to find the best way to do this to minimize the cost of building the pipeline. Okay, so this is again one of those scenarios where you definitely want to get a good diagram in. So let's get a river here. So we've got a river. It's 1 kilometer wide. Okay. And the pipeline has to go from point A, from one side of the river, then it's got to cross the river and go 8 kilometers downriver. So I'll put B there. So we have this distance is 8 kilometers. Okay, and you can build this pipeline either across the water or you can build it across land. Okay, so it looks as though our constraints here is that in terms of minimizing the amount over water is to go straight across and then along land, which maximizes the less expensive version, or you can go straight across, which gives you the shortest distance, but goes along the water the whole way through, which is more expensive. Okay, so what we want to do is we don't want to use one of those special scenarios when setting up our problem. We want to take a more typical scenario. So let's say it goes partly underwater and then partly on land. Okay, could have gone on land and then by water, wouldn't have made a difference. Okay, so let's see how we're going to set up this problem. So essentially what we need to do is we need to figure out an expression for that distance and then an expression for this distance here. So I'll call this distance along the water. I'll call this distance on land. Okay, and then I'm going to multiply the cost to this distance for the water and multiply the cost for this distance along land. The only thing is that they don't give us the actual cost, okay, but they tell us that along the water it's 1.6 times more expensive. So what I'm going to do is I'm going to say let CL be the cost on land. Okay, so then CW, which I'll say is the cost on water. Okay, CW is going to be 60% more than that one there. So in other words, 1.6 times the cost on land. Okay, so what we're doing is we're going to try to minimize the amount of variables that we have to use. Okay, so what we need to do is determine expression for these distances with respect to one variable. So I do notice here that I can create a right angle triangle. So it looks like I'm going to work with Pythagoras on this triangle here because I'm looking for an expression for this distance. I know this side of the triangle is equal to 1 and this side of the triangle will be related to the 8 kilometers. Okay, so what I could do is I could conceivably call this x and then this would be 8 minus x. Okay, now that's one option and it's nice because this x value will be exactly one of the values that I'm trying to express here, which is the distance along land. But the problem with doing it this way, and if you did it, it'd be perfectly fine, but I notice I'm going to have 8 minus x inside this Pythagorean expression. Okay, so to make my life a little easier, I'm not going to express it that way. I'm going to call this little part x. Okay, and then dl is going to be 8 minus x. So it means this expression is slightly more complicated, but 8 minus x is still a fairly simple expression. And what that does is it makes my expression for the distance along the water much, much simpler. Okay, so a little trick that we use here to make our equation simpler. Okay, so let's come up with our formula here for the total cost. So the total cost is going to be the cost along the water times the distance along the water, okay, because this will represent the cost, per, say, meter, I guess, or per kilometer in this case here, okay, plus the cost on land times the distance along the land, okay. So let's now start inputting using the variables that we have here, so we can minimize the amount of variables that we've got. So we said that the cost along the water is going to be 60% more than the cost on land, so we already established that. And the distance along the water, well, I can express with respect to this variable x. Okay, it's just going to be the square root, because it's the hypotenuse of the triangle, of x squared plus 1 squared. Okay, and then here I've got CL, the cost on land, and the distance on land can be expressed by 8 minus x. Okay, so what's nice is that I've got an equation in terms of x. Now you might say, well, I also have this CL, the cost on land, but that's just a constant. Okay, so I'm going to leave that in there because I don't think that's going to affect how I'm going to solve this problem here. Okay, the main thing is that I was able to express the two distances, the things that can change, okay, with respect to a single variable. Okay, so at this point here, I'm going to take the derivative of the total cost. Okay, so here again, 1.6 times CL is just a constant. Okay, so now I'm going to take the derivative of this function of x, so it's just 1/2 x squared plus 1 to the negative 1/2 times the derivative of x squared plus 1 is just 2x. Okay, and then this here, well, if I distribute the CL to both, the CL times 8 is just going to be a constant, so when I take the derivative is 0. So I'm just left with the derivative of CL times negative x. So that's just going to be minus CL, because the derivative of negative x is just negative 1. Okay, so here's my derivative, and of course what I'm looking for are the critical points, and so I'm trying to find a minimum value here. Okay, so I'm going to set my derivative to 0. Let's clean this up a bit so the 2's cancel out. So I'm left with 1.6 CL, and then here what are we left with? We're just left with an x in the numerator and the square root of x squared plus 1 in the denominator because of that negative exponent. Okay, minus CL. Okay. Now, this is where we're going to prove that we didn't actually need to know the cost of the pipeline on land, because now I can just divide CL to both sides of the equation. It'll cancel out in this first term and cancel out in this second term. So what I'm left with now is just 1.6x over square root of x squared plus 1, okay, minus 1. Okay, and this is actually not as bad as it might look to solve. Okay, so let's do this here. So I'm going to treat this like a rational expression. Okay, even though I've got this square root, I want to write this. Anytime I want to work with something that's rational equal to 0, I'd like to put this as a single fraction. Okay, so I'm just going to add or subtract these using a common denominator of square root of x plus 1. Okay, so the left term already has that denominator. I'm going to have to multiply the 1 by square root of x squared plus 1, and then over square root of x squared plus 1. Okay, now since this is a fraction equal to 0, I'm only interested in the numerator being equal to 0, or I can think of multiplying that to the other side and just becomes 0. Okay, now this is where I got to figure out how are we going to solve this equation. Okay, there's no algebra we can really do to factor anything out. So the trick is well, we bring the term with the square root to the other side of the equation. Okay, and now what we're going to do is just square both sides. Okay, so if I square the left-hand side, I just left with x squared plus 1, very nice, and squaring the right-hand side is pretty easy. So 1.6 squared, so 16 squared is 256, so this will be 2.56 x squared, and I end up with something very easy to solve. So bring the x squared to the other side, so I'm left with 1.56 x squared, and so x is going to be equal to the square root of 1 over 1.56. Now, of course, the only reason why I'm taking the positive square root alone is because x represents a distance, and so I'm not interested in anything negative. So let's calculate that here. So we've got 1 divided by 1.56, and let's take the square root of that. And looks like, oh, it's a pretty nice number, so we'll just take 0.8. So x is equal to approximately 0.8 kilometers. Now, of course, what we have to do is we have to show that this indeed gives a minimum cost. Okay, so a couple of things we could do. And first thing that I should have done at the very beginning is when I came up with my equation, I should have seen what the constraint on my variable was. So I should have done that earlier. So let's do that now. Okay, because I see that at the very least, you know, x can be equal to 0, because if it's equal to 0, it means it comes straight down and then across. Okay, and the other option is that x is equal to 8, meaning this is just going to go straight across the river all along the water. Okay, so here x has to lie between 0 and 8. Okay, so we have a closed interval, which means that when I'm determining my max and min, I could just test the value for each of these and see which one gives us the largest. Okay, the only problem here is it's a little tough to actually test it since I don't have the cost on land. So for this one here, I am going to do it by determining the sign of the derivative to see if it indeed gives us an absolute minimum. Okay, so I'm only interested between 0 and 8. Okay, my only critical point is at 0.8. Okay, so let's take the derivative function here. So since I'm only interested in the sign, let me work with this expression here. Okay, because I notice what I had in the denominator is always going to be positive, so I'm just going to work with this one here. So let me put in 0.5. Okay, so 1.6 times 0.5. Okay, and then minus, I'm going to take the square root of 0.5 squared plus 1. Okay, so take the square root of that. And I end up with a negative number. So that means that between 0 and 0.8, since it's the only critical point, it's always decreasing. So now let's pick something between 0.8 and 8. So let's pick something easy. Let's pick x equals 1. Okay, so here we have 1.6 times 1 is 1.6 minus the square root of 1 plus 1, so square root of 2, so minus the square root of 2. And here we have a positive number. Okay, so in this interval, okay, it's always decreasing up until 0.8, and then it's always increasing all the way to 8. So this must be an absolute min, okay, on this interval. Okay, that's all we can say, but that's all we care about is on this interval, it's an absolute min. Okay, so now we go back, and I go back to the problem, and it says find the best way to cross the river so that the total cost of the pipe is kept to a minimum. Okay, so I need to use this value of 0.8 to describe how to do it. Okay, so I guess what I'm going to do is I'm just going to draw a picture. So I go back here, or I could explain it in words. So from A, I'm going to go across the river so that this distance is 0.8. Okay, and then so like that, and then I'm going to go to B, and so this is going to be a distance of 7.2, and I should put the units kilometers. Okay, so this would be the best way to cross the river. Now, had I given it in the other way, that if I had done 7.2 and then across the river, so that little portion was 0.8, that would have worked also. Okay, so let's recap. Number one, how to set up the problem. Okay, very typical type of problem that, in fact, we saw there was a very similar one to this that was posted last week. Not to worry about the fact that we didn't actually know the cost per kilometer on land because we knew the relationship between the two. Okay, so we were able to write an equation with that cost unknown, and then we realized that it didn't make a difference. Once we took the derivative, we were able to just divide it out from both terms. Okay, and in terms of actually solving, so this is, the algebra perspective is, as usual, anytime you have fractions, rewrite it as one single fraction. And here we're seeing that when we've got a scenario where we have a term that has a square root and one that doesn't, bring the square root to one side so that you can square both sides of the equation. Okay, and I think that's it for this one.